Hey everyone, welcome back to Daily LeetCode channel. Today's LeetCode Daily Challenge is problem 3577. Count the number of computer unlocking permutations. Let's read the problem carefully. You're given an array called complexity of length n. There are n locked computers in a room, labeled from 0 to n-1, and each computer has its own unique password. The password for computer I has a complexity value, complexity I. Now here's the twist. The password for computer 0 is already decrypted, so computer 0 acts as the root, the starting point. All the other computers, 1 through n-1, must be unlocked using computer 0 or any other computer that has already been unlocked. And the problem defines the unlocking rule very specifically. You can decrypt the password for computer I using computer j, if j equals I and complexity I equals complexity I. In other words, to unlock computer I, you must have previously unlocked some computer j that has a smaller index and a lower complexity. And of course, that computer j must already be unlocked before you attempt to unlock I. Your task is, find how many permutations of 0, 1, 2, n-1 represent a valid order in which the computers can be unlocked, given these unlocking rules, and starting from computer 0 as the only one initially accessible. Since the number of valid permutations could be very large, the result must be returned modulo 10 power 9 plus 7. And one very important detail, computer 0's password is decrypted, meaning the computer whose label is 0 is the one that is initially unlocked. It does not refer to the first element in the permutation. It's always the computer with label 0 that is unlocked from the start. That's the full problem description. Next, we'll go through some examples to understand it even better. Example 1. Input complexity equals 1, 2, 3. Output 2. Let's break down why the answer is 2. We have 3 computers, 0, 1, and 2. Computer 0 is already unlocked. Complexities are increasing from left to right. There are 2 valid unlocking permutations, 1, 0, 1, 2. First, we unlock computer 0, it's already decrypted. Next, we unlock computer 1 because complexity 0 is less than complexity 1. Text 1 less than 2. Then we unlock computer 2 using computer 1. Complexity 1 is less than complexity 2. 2 is 3. Everything follows the unlocking rules, so this permutation is valid. 2, 0, 2, 1. Again, we begin with computer 0. Next, we unlock computer 2 because complexity 0 is less than complexity 2. Finally, we unlock computer 1, also using computer 0. Complexity 0 is less than complexity 1. This sequence also satisfies all the constraints. So in total, there are 2 valid unlocking permutations. Example 2. Input complexity equals 3, 3, 3, 4, 4, 4. Output 0. Here, multiple computers share equal complexity values, and that immediately creates a problem. The rule requires complexity j equals complexity I for some j less than I that is already unlocked. But look at the array. Computers 0, 1, and 2 all have complexity 3. Computers 3, 4 have complexity 3, and 5 all have complexity 4. For computer 1 to be unlocked, we need an earlier computer with strictly lower complexity. But computer 0 has equal complexity, not lower. Same problem for computer 2, 3, 4, and so on. Because this condition fails immediately, no computer beyond 0 can be unlocked. Therefore, there are 0 valid permutations. All right, let's explain this concise solution for 3577. Count the number of computer unlocking permutations line by line and prove why it works. Here's the code we are explaining. Problem recap, one-liner. You start with computer 0 unlocked. A computer I can be unlocked only if you already have some unlocked computer j with j less than I, label-wise, and complexity j less than complexity I. Count valid permutations of labels 0 to n-1 that represent an unlocking order. Modulo 10 power 9 plus 7. Early sanity check. Why the code checks every element against first. First is the complexity of label 0, which is the only computer unlocked initially. If there exists any label n greater than 0 with complexity m greater than first, then there is no way to ever unlock that m. Why? Consider the leftmost such index m, the smallest index greater than 0 with complexity m greater than first. For any j less than m to decrypt m, we need complexity j greater than complexity m. But by the minimality of m, there is no earlier index j with complexity j greater than first. Hence, no earlier j can have complexity j greater than complexity m. In particular, j equals 0 has complexity 0 equals first, which is not less than complexity m. Therefore, m has no valid unlocker among indices less than m, and it can never be unlocked in any permutation. So the total number of valid permutations is 0. That's why the solution immediately returns 0 when it finds any complexity I greater than first. Visually, show a timeline with indices and highlight the minimal offending index. Point out there is no allowed j before it. Counting permutations when all complexity I greater than first. If we make it past the loop, then complexity I greater than first for every I greater than 0. That means, for every label I greater than 0, the label 0, which is already unlocked, has strictly lower complexity and satisfies 0 less than I. So computer 0 can be used to unlock any computer I greater than 0 at any time. Because 0 is always available as a valid unlocker for every other computer, there are no additional constraints interfering with the relative order of the other labels 1 to n-1. Any permutation of those n-1 labels can be realized. When a label appears in the permutation, we can simply decrypt it using computer 0, or any previously unlocked lower complexity label, but at minimum, 0 always suffices. Therefore, every ordering of the remaining n-1 computers is valid. The number of such orderings is n-1 expression. Computing n-1 expression, modulo 10 power 9 plus 7. The loop multiplies 2 times 3 times 11. All multiplications are done modulo mod equals 10 times 9 plus 7 because the problem requires the result modulo that prime. Edge cases. If n equals 1, then the loop range is empty and fact remains 1. There is exactly one permutation, 0, and returning 1 is correct. If n equals 2, the loop multiplies I equals 2 times 1, empty. So fact equals 1 fact, which is correct. With one other computer, exactly one ordering of the remaining single label exists. Complexity and summary, what to say at the end. Time complexity, ON, a single pass to check the condition, and a short loop to compute factorial. Space complexity, O1, only a few scalars are used. Summary to narrate. If any computer has complexity less than or equal to the root complexity at an index where no earlier label can unlock it, the answer is 0. Otherwise, the root, label 0, can unlock every other computer at any time. So all permutations of the other n-1 labels are valid. Thus, the answer is n-1 expression, modulo 10 power 9 plus 7. All right, moment of truth. We've coded the solution for count the number of computer unlocking permutations, and the logic is pretty elegant. As long as every computer after index 0 has strictly higher complexity, the number of valid permutations is simply n-1. So let's hit run and see what happens. Okay, sample test cases passed. That's always a relief. The logic is checking out. Everything looks consistent, constraints respected. I think it's time. Here we go. Submitting. Accepted. There it is. Green checkmark. Our ON solution handled everything. Clean, fast, and mathematically tight. We successfully counted all valid unlocking permutations by recognizing the strict increasing complexity condition and applying factorial. If you found this breakdown helpful, hit like, subscribe for more daily LeetCode guides, and drop a comment if you want me to cover the editorial, an optimized approach, or a completely different problem next. Thanks for watching. See you in the next one.